Yeah, this is Anu. Thank you, Anu. So as you know, this is Swasth, so this will finally be made a public video. So we're just recording so that we can share it with others as well.
Anu
Good.
herself
So,
is not being seen.
sorry?
I'm saying Anu herself is not being seen while she's complimenting your look.
She's off video. That's okay. Good. Chalo. We'll get started. Yes, everyone good. So we'll start with our, in the normal way, we'll start with our prayer. But I finally, by the end of it, sort of decided to also change the title. I think I felt like the chain of science wasn't that interesting. So the language of nature is what I've decided to now title it. And hopefully by the end of this session, we'll see a little bit where that title is coming from. So we have more people joining in. Thank you. We'll start with our prayer. So just sit comfortably, setting the intention for the session as we start. Ground ourselves. Just let your feet be comfortably on the floor. If you're on a chair, just sense the floor. Let your back be supported. Gently close your eyes. Bring your attention to your breath at the nostrils. Just notice the air going in and out for a few rounds. And repeat after me. May we be Saath together.
May we be Saath together.
May we be Jigyasu, curious.
May we be Jigyasu, curious.
May we be Virya, energetic.
May we be Virya, energetic.
May our learning be Tejasvi, bright.
May our learning be Tejasvi, bright.
Shanti, Sukoon, peace.
Shanti, peace.
Okay. Good. Good. Thank you everyone for joining. Hi, Prateek, Malesh, Pushkar, Amruta. Thank you for joining. So we'll start with our session. So we can name the session as Chain of Science or the Language of Nature. And as I said, we'll start with looking at some patterns in nature. So today the intention is to start with biology or what we see of life around us. So I talked about obviously in the message just now about cheetah, the stripes of cheetah, the spots of cheetah, the stripes of a zebra. Those are some of the patterns, and this is a very similar things we start seeing in fish, water, snails. So these patterns keep coming up, right, in nature. And so what we'll try and today do is take this journey into trying and understand how are these patterns emerging. What is different, firstly, about these patterns? So maybe anybody, what do you see is different in these patterns? Right, or imagine other patterns like the stripes of a zebra.
Put it on here.
Yeah, Kalpesh, Anu.
They all, most of them look like waves.
Most of them look like waves. Okay, so that's what's similar. Good, thank you. That's important. Okay, how are they different or similar? Yeah, Anu, you're saying something?
No, sorry about that.
Okay. No. Others, what is similar, what is different in patterns that we see in nature? Yeah, Pankuri?
They are colorful.
Yeah, the colors. So they're different also, right? Colorful means they're different. Oftentimes each has like contrasting, right? Zebra will have a
Yeah.
black and a white and a yellow, and here also we see that. Yeah, there is difference in that. Okay.
Most
They
of
are
the
really-
time they are like two colors.
most of the time they are two colors. Yeah. Okay. Good.
See, some of the patterns have a source, and some of the patterns don't have an ending or a source.
Okay. They seem to be starting and ending in some and some sort of carrying on. Sanjeev, we couldn't hear you. Okay, Sita
There
is
is,
saying concentric circles.
can you hear me? Can
Yeah,
you
now
hear
I
me?
can. Yeah,
Okay.
now.
There is some kind of center for each pattern, it seems like.
There's some kind of center. Chaya is saying symmetry.
Yeah,
Good.
symmetrical.
Yeah. So there are lots of things which seem to be common, but they are also still very diverse, right? They're so unique, each one of them in their own way, including sort of our fingerprints. If we see, they're so unique and distinct. So I'm going to show you, take you to a website now, where we'll see like how they are formed, and then we can talk about what's different maybe a little bit more. So let me share that screen with you. So the link of this thing will be there in the PPT when I share that. So you can also play around with it. So you can see this site, this pattern here. Everyone? Yeah, you can? Okay, good. So now you're seeing a certain pattern, right? So let me change this. If I clear it, so you're seeing it's changing, the dynamic part of the pattern, that it's changing, shifting. Let's give it some time. So there was lots of spots, right, earlier. Yeah, are you seeing it change? Yes, shifting, yeah, the dynamism, yeah. So it's changing. So let me clear it. Okay. Now we'll start playing with this like this. Let me just create some random spots here. Let's see what happens. So from beginning, what happened? Did we get to the same place almost very quickly? Very similar. Yes, the pattern. Yeah. Okay. So let's shift this. Let's see now in this also. I'm just changing this. So this change here is like changing some parameter. Right. And let's try this now. So anybody, what are you noticing in these various things? What's happening? Anybody
There are
can
more circles at the edges, right? Like when you pulled it to the side, like it's like that honeycomb kind of thing towards the edge.
Yeah.
Lot
Yeah.
of-
But yeah, in center it's like this, right now.
Yeah.
Okay. Anything
The
else?
center seems to remain constant.
Constant
Pattern.
right now.
So starting from any source, it seems that it is growing into something same,
Same.
Yeah.
irrespective of how you started.
How you start.
Yeah.
Okay. Pankuri?
It's moving. It's continuously growing, evolving into something. It's not stagnant.
It's not static. But at this point, it is remaining quite stable, right? At some point, like it becomes quite standard, yeah. But it's still different. Okay. So let's try this.
Mm.
Are you noticing some change now?
Yeah.
Yeah. So the reason I'm showing this is a simulation, right? Which typically means on the back end, there is a it's the same math that is operating, but it's sort of by changing some parameters. Now there are no spots, right? Spots are gone. It's like from the cheetah, it's become something else. Now there's some other labyrinth, a very different, unique pattern that emerges. Yeah. Okay. Let's try this. I'm also playing randomly with these. So these are the two sort of variables in this structure. And you can see that what this is doing is there are different kinds of structures here. And that sort of results in a similar pattern, or they contribute to that. If I change this parameter, you can see automatically, even from that so-called almost static, it will start changing. And the entire structure of the pattern that starts emerging over time is kind of quite different. Well, I'll take a pause, see what is going through your mind as you're seeing these variations with just change of these bubbles. And I think you can play with it. Definitely, I'll share the link. Link is there anyway. So what's going through people's mind as you're seeing all this? Whatever you are seeing, I'm sure something like this is there in nature, right? Either somewhere you would have seen there can be a snail like this. It's not like some Atrangi artistic pattern. It's just what we see in nature, in either a fish or a bird sometimes, in animals, in formations also. Sometimes you find microorganisms together like this. All these shapes and all do happen. So what's going on in your mind as you're seeing this?
I think this is process of evolution. Everything started from water. So I think that it is related to this.
You're seeing it like a process of evolution, okay?
Yes.
To me, it's like, what we think is static is actually not static. There is movement happening. We may see it, we may not see it, but something is constantly changing.
Something is constantly changing, yeah, evolving, okay.
Also, you feel some kind of balance. There is balanced structure, even if it may not seem very, like if you see up close, it may not seem, but the bigger picture you see, there's some kind of balance.
There is some kind of balance, yeah.
Nature is the best piece of art.
Nature is the best piece of art, yes.
See,
It's like
initially
when
the
you
changes
watching
are.
it. Sorry.
Go ahead.
So Malesh, then Bhuvna, there was one more voice. But okay, go ahead, Malesh.
Initially, the changes are very stark and significant, but later on, the changes are only in certain portions and minor. If we look at, same time interval, that is, let's say, if we look at it every 2 seconds or so, but later on in that 2 seconds, the changes are very minor.
Yeah, initially change is quick and then it becomes lesser. Speed is okay. Yes, Bhuvna?
Yeah, I'm talking from my perspective, I see how my system is slowing down just watching it. Feels like a nice stress buster,
Yes, this can be. And so it can be very playful also, right? Now if I change it here.
It's also like when you look at a tree up close, like under a tree, you see branches going here, there. You don't see any organization. But if you see from far, tree looks very, very symmetrical.
Nice. Yeah. Okay.
Very balanced.
Zooming out,
It reminds me of that.
Okay. Chaya says, feels like meditation, peaceful despite constant change. Wonderful. Yes. Good. So, yeah. So now let's step back and go back to our original question a little bit. So this is what we have seen. Now we are seeing these patterns, right? So my question is, what makes this different? The colors, the patterns different. What is driving this at a fundamental level in nature? Now coming back to, okay, something is yellow, something is white, something is black. What is causing those color differences? What is causing these pattern differences? This is simple
Adaptation.
Adaptation. Okay. So yes, so adaptation is the macro cause, the micro cause. Like when I zoom in under a microscope, what do you think I will see being different? Adaptation probably caused that to happen, but what changed because of adaptation? Just saying spacing, size, shape. Yeah, those are the different things we are seeing. But what is causing it? So very actually simple answer: the chemicals. The chemicals are different. The pigments are different. Right? So just very different chemicals will react differently to a light. So if you even see, for example, paints, what differentiates a blue paint from the pink paint? They are fundamentally the same, right? It's just a pigment, a chemical which is different. I don't know, recently have you bought or maybe never gone to a paint shop and bought paint? Now what they do, they have a white tumbler full of white paint. So you go there and say, I want this particular pink you see on a screen, and then they will click it. And accordingly, a mixture, a very little liquid of that will come and get mixed with the white paint. And it will give you that blue, pink, whatever shade you want. Right? Because that's the extra pigment which is changing the color fundamentally. Because reflection of light is different. That's what makes like dyes in our clothing also, right? What makes a red color, etc. So pigments are different. The colors itself, the chemicals are different. The chemistry is different in some ways. And what other thing which is different, which results in these patterns, they found was some physical properties of these chemicals, which is what I think Malesh was a little referring to, like how fast they can spread, how fast they can diffuse is the word that is used. So what is diffusion? One simple example of diffusion is, again, take a tumbler of water, you drop just one drop of ink. What happens? Initially, it will go very fast, right? It will just zoop to everywhere. And then it settles. Exactly what we're saying, right? It goes very fast. That's diffusion. It's diffusing. There is no force. Just by random movement, it has to spread so that it's evenly spread. The goal intention is that there is even spread of that extra blue color that we have added. Same happens with paint. When I add that little bit of white color in that white paint, 1 liter of white paint, it will spread to the entire paint so that the whole thing becomes blue. That is diffusion. So some physical properties are different. So we'll look at it a little bit more in detail, what is really happening here. So let's look at the chemicals. I'm not going to name the chemicals, but there is a chemical. Ligand means a chemical U and chemical V. There are two kinds of chemicals, the red and the blue ones, right? What are their properties? That they can go and bind to a cell which is there in our biology. And the technical ligands, for people who know, they go and bind to this cell. Like you can see here, it is binding. It just gets attached. And there are two kinds. Basically, one, what they do is, so they can move around, they can diffuse, move randomly in space, and their diffusion rates are different. The speed at which they diffuse is different. That is different for each chemical. And when they bind, they will either enhance or repress the production of themselves. That is their nature. So one of these, when they attach, they will increase, the U will increase its own production. And when this attaches, it reduces the production of everything else. That's their nature. That's how they are different. So this is the nature of those chemicals. This is how nature made it. There are just two kinds of chemicals. They are often known as excitatory or inhibitory also. Right? So something which excites or increases, enhances, and inhibits or represses. Right? In the nervous system language, that's how it's used. Inhibitory and excitatory. So we see this in daily life. There are some people who energize us, some topics that energize us, and some things that shut us down. And unfortunately, sometimes science shuts people down. So I don't want that to happen. So trying to keep it very simple and make sure, stay with me. We're trying to keep it very simple, not getting into too much detail, but just know that there are these two kinds of things, something which appeals and something which doesn't. That's how cell is a living entity like us. So some things the cell likes and something it doesn't, right? So there are two kinds of chemicals which will attach. What likes, it will increase. What doesn't like, it will decrease. Yeah. Enhances or suppresses. It increases its production or reduces its production. So for example, in a pattern, a white chemical or a black comes, and if it enhances, there will be more black, right? But then it will also enhance the white production, the opposite. And that's what we will see. Then, but the white's nature is what? That it will suppress. It will suppress everything now. So there is something which increases. So it increases both, and something then that suppresses. So it suppresses others. And that's why somebody was saying there is some balance, some equilibrium, some fight in some ways, right? Some dance that is going on between two things. Yes, Jay.
So does the cell have a mind of its own? What it likes and what it doesn't like?
Of course. There are very clear things defined in cell. That's actually one of the amazing properties of cell. That's how they survive. So imagine a bacteria cell which is surviving on its own. So it knows, right, what I should consume. It is taking energy, nutrients. So its boundary, its cell wall, is a semi-permeable membrane. It's a very intelligent membrane. It knows exactly what it needs. And the waste material that it generates, it knows what to throw out also. Like it won't throw out its genetic material, but it will throw out the waste that has come after its respiration. So cell is very intelligent. I don't know whether it has a mind. So mind is a tricky word, but it is intelligent. It takes some decisions and it acts according to those decisions. That's the only it survives. So cells, for example, also detect concentration of food that they like, and they direct their motion in that direction. Like a bacteria, what it wants to consume in a lake, in a pond, if it is able to sense where what I want is there in that pond, and they will start gravitating towards that. Even externally, they do sense that. Does that answer, Jaya, the question?
Yes, to an extent, yes.
Did I freeze for some time? Seems like. Can you hear me? Yeah. So, Jaya, that did answer your question about the cells?
Well, that's one perspective which I'm taking for now. So, yeah.
Okay. So, Bhuvna's added, Bruce Lipton, who is an MD, says that the brain of the cell is in its cell membrane. Yeah, that's interesting. Okay. Any other questions on this? On the two kinds of chemicals, that's at the center of this. There is chemistry, the nature of those chemicals that is there. Now, what happens because of these two? So remember the two properties of these chemicals, they bind, and one of them on binding increases the production, enhances, and the other reduces, suppresses. Okay. And they move around freely. So they will bind here, they'll go to another cell, they will move. As more is produced, they will start spreading. Right? That's what we were seeing in those simulations also. Right? That they were spreading. Even if I have one, it will start spreading across whatever space is left. Now, and their rate of spread is different. These diffusion rates are different speeds. Just like different cars have different speeds, different humans have different speeds. Similarly, different chemicals have different speeds at which they move. Now, so this is what really happens, the physics part of it, right? The physical movement and how they are managing. So U is, let's call it the activator, and V is the inhibitor. So this is showing at the start of time, right? Let's say this is the concentration. So I have this much V and just slightly more U. And in this point, there is a slight hump in U. There's slightly more U. Now U is the activator, right? So what will happen? If there is more U, it will generate. So there will be an increase of both U and V. At this point, both will start increasing and they will start spreading. So because there is more here, they will increase more and they will start spreading also at their own speeds. So the reason you see this difference is because their speeds are different. You can imagine, right? Suddenly from 1, 4 have come out at this point in the center of this box. This is the box, right? So then 4 have come out and they have started spreading like this, right? Then from 4, 8 has become and they are starting to spread like this, right? So what does this tell us? Which one moves faster, you think? U or V, based on this graph? What can you say? Which is spreading faster? The fixed line or the dashed line?
The dashed line, no?
Yes, it's moving faster, right? That's why it spread more, right? So that's where the difference in their speed starts making a difference. It's very important. This property of their just that they move at different rates, right? So after some time, it starts looking like this, right? Because they have spread. Now what happens is, now suddenly the concentration of this is become very high, the inhibitor. So what will happen? The inhibitor starts increasing and it starts reducing even the activator, the U. So in this area, there is more inhibitor. So the concentration of this starts falling down. Even the A, the activation. And slowly, you will start seeing some pattern emerging just because of this seesaw happening. One goes up. So as the inhibitor comes down, again the activator will increase. Then the activator will activate the inhibitor also. So then inhibitor will go up. So then the inhibitor will again reduce both. And because their speeds are different, it will happen at different places, this cycle. Right? So you're already seeing stripe-like pattern coming, right? In this. This is how this dynamically will happen, slowly. And this is the physics, because this is the movement, the rate at which they are moving. And the chemistry, because the way they are reacting. So both physics and chemistry are coming here very beautifully to create these biology patterns in biology that we see. Right? So the life that we are seeing out here, the diversity, it's coming because of the diverse chemicals. And at the background is this beautiful phenomena of how fast they move. Just that. Being different is bringing such amazing things. Right? And the different chemicals is giving the different colors, the variety of colors that is there. Is it making sense till now how this is happening? I've still not gotten into any math yet. So that's why this is still, I think, very plain, simple English. I'm trying, besides the word diffusion, I'm trying to avoid any. But diffusion is just imagine the ink spreading through the water. Right? That's diffusion. When you put a drop of ink, it'll just go. Try and think of other examples also. Any other examples that people come to mind for diffusion? This is how this is spreading at different rates. I'm trying to think of. So I don't know if people have tried this, but if you were to take the same drop of ink and put it in oil, do you think it will move at the same rate? No, right? I'm seeing now. Yeah. So it depends on what fluid you are putting that in. And now instead of ink, if I put honey in water, will it spread at the same rate like the ink? Or does honey flow differently in water? Faster or slower than ink?
Lower.
Lower, right? So exactly like that. Like there is ink and there is honey. So they are moving at different rates. So if I put them both together, after some time, if I see, they will start separating, right? The ink will look different and honey will look slightly different. And now if they start interacting, it looks very, very different. And that's what's happening here, that they are also interacting. There is a reaction. And that's why this beautiful dance is happening, which is resulting finally in these patterns emerging. Does that make sense? Now I'll maybe show the simulation again, and if you correlate it with this, maybe it will help, right? You want to see the simulation again, that those things now, how that interaction is happening? or no? Yes, yes, Bhuvna.
So I'm just trying to understand this whole phenomena. So suppose I drop both water and honey into, drop a drop of ink and say honey into water. Then they start spreading at different speeds, and that can kind of produce different patterns.
Yes. So if you do that, now if you start seeing, let's say you see after 1 second, you will see a certain way. At 1 second, probably they'll be very close. Then you see after 5 seconds. Now the honey has moved, spread only this much, but ink has this much.
Ink has spread.
So you will see it differently.
Yeah, yeah.
And then after 10 seconds, probably the whole water has become blue, but the honey is still just here. So you will start seeing honey in a background of blue.
So can we kind of consider you and we as the ink and honey?
Yes, in some ways. Yes.
Okay. Like I'm just trying to get
yes.
into my
No,
head.
thank you. Yeah, there's something like that. The only difference between UV and this, in terms of speed, yes.
Yeah.
But the difference is U and V also play another role, that U activates and V inhibits.
Yeah.
So now imagine you put an ink which activates. So suddenly it's spreading and everywhere there is more ink.
More ink. Yeah. So it's creating like
but,
a
correct. Exactly. And now honey is only in the center. It is inhibiting. So what will happen? From the center, all the ink will go out. So wherever there is honey, you will find, oh, there is no ink. The water is crystal clear. But where there is no honey, it's blue. The ink color has come into water. Right? And then you add another drop of honey someplace else, that will again very quickly become like that. So then you will start seeing a pattern of blue water, honey, blue water, honey, like that.
Okay.
Something like that. That's good. I hope, yeah. Does that make sense now? More? Yeah, Pushkar is, yes. Clearer? How that can happen?
Yeah.
At any given point in time, the activator and the inhibitor both move.
Yes.
At different speeds. It's not that one is static and the other is moving.
Yes.
It's not like that, right?
No. Both will move. That's the law of nature. Both will diffuse. Just the rates are different. Exactly. And based on their concentration, if one goes up in one place, it will either inhibit more or activate more. And that will start causing this difference in that pattern emerging. Like the honey will take away the ink in where it is in very high concentration. So the water will become clear there. Because it won't allow that ink almost, or very little ink will be left. The rest will go out. That's what it does. It reacts to change that.
Sandeep, any examples of U and V in terms of biochemicals that you know?
To name many. So any pigments. Many pigments. So these are what makes it different. So this simulation, that's why I'll take you back to that simulation again. Now see it with this lens, because these are the two chemicals here now, right? Different. So this blue and yellow are essentially two chemicals. In this, they have made it simpler. They are saying this property of the chemical, you see here, right? K and F. This is what will change. Now, if I move it here, you're seeing this K and F change. Kf is the reaction rate and the diffusion rate, and it changes the kind of pattern. See, the blue is here. So this has a tendency to spotify. That's the kind of chemical that it is. So if I change this to here now, see, this spotification will go because it will diffuse faster. So spotification happens when diffusion is slower. As soon as I spread, now it will start joining. And you'll start seeing slowly the spots are going to go away.
So K and F represent the property of the chemical.
K is the reaction rate, F is the diffusion rate. Yeah. Those are the parameters. Now we'll come to that's what mathematics helps us provide finally.
But any biochemical you can name, or maybe?
Yeah. You can find any biochemical, any chemical, you will have these properties, right? Okay. The reaction rate between the two and the diffusion rate. You're seeing the dots are going slowly. The spots are gone, right?
Yeah. So K is the reaction rate, you said.
How fast the reaction can happen.
Reaction between
that binding that is happening, how quickly it will attach to the cell, how quickly it will inhibit or enhance. Enhance, yeah.
Enhance. Okay. Okay.
Seeing almost spots are now just left here. All is gone. We've had spots, right? A lot. This will also go. Now you can zoom in on this area and see how the spots are going slowly, how they start attach because they diffuse, they are spreading, and then they will react and attach, and it will form a stripe. From two spots will become a stripe. It's like joining the dots.
Mm.
So zoom on this bottom left. You will seeing that action.
So the K and F varies between for a cheetah versus a tiger.
Yes, the chemicals are different. Exactly. But they are similar in that yellow or that color zone. But even I think between a cheetah and leopard, they are different. And then it differs. Apparently, now they are saying that you can identify a leopard or cheetah by the spots. It's just like the fingerprint. It's
No, I'm
unique for
talking
every
about cheetah and tiger.
I
Cheetah
know.
and leopard is too close. Like I'm just
Yes. No. Cheetah, tiger, definitely. Yes. That is there. I'm saying even between two cheetahs, like cheetah 1 and cheetah 2,
yes.
the parameters are the still same, but the pattern becomes very unique still because the starting points are still. But the nature of the spots or stripes is very same. You're right. Yeah, the cheetah and tiger is a good example. It's very different. And with the zebra also, zebra is more uniform, right? It's continuous, long lines. Tigers are like this, more labyrinth, maze-like. Yeah, again different. Yeah, these two people will keep seeing, I think, meditative. But I hope you're seeing, right, how this is all converging. Let me see if what will this do. Does it change? This changes the speed now.
Mm.
We will create longer lines. So if I go in this zone, see how more empty space is getting created now, right?
Created, yeah.
Because that's the property. The K and F has changed. See, so quickly, this is Spotify. And like again, first the change is very fast and then it slows down.
So when K and F, they reduce, it becomes more like a spot.
Yes, what you're seeing here, right? See, both are here. There is simple pattern.
Mm.
And still, see, there is movement here. You're noticing it's not static.
Yeah, it's. Mm.
And this is where the coagulation will happen bigger. It will make bigger blobs because their cohesion and sort of the way they are reacting, adding to each other is big. So those are the properties. So play with it. Okay. So I'll stop this and see if there are any questions, comments on how this is sitting now. Is this, at least physically, is the process clearer on what is really happening, right? And what is different and yet what is same between different patterns. Everyone? Pooja, Sita, Kalpesh, Gopesh, yeah, Pankuri, Madhuri, Mruta, good? Anu? So now, this is what was seen, and this we know now a lot in retrospect. Sort of the journey was slightly different. I'll take you through what happened, how we came to this understanding a little. And there's still some, one can say, debate or jury still is out there because in biology it's very hard to finally conclude everything. So this is what is known as the reaction diffusion model, and that's why the K and F parameters are there. So this was in 1952. This paper started. And this was by a very person called Alan Turing. I don't know if people know of Alan Turing. Have you seen? So Turing is known as the father of computers. So he was a computer. He's the guy who developed the theory of computing. I think he's also the guy who cracked the German cipher in World War II, and the movie is made on him. I'm forgetting the name of that movie, a Hollywood movie. Oh, this guy is there, Cumberbatch. Does anyone remember? No. So this is which one? Which movie, Sandeep? You know?
No, I'm also trying to look up. I don't remember the movie.
It's the Imitation Game.
Yes, Imitation Game. Yeah. So Alan Turing, like the Nobel Prize in computer science is named after him. So that's the way to know who he is. So computer science doesn't have a Nobel Prize. So the Nobel Prize in computing is named after him because he's sort of the guy. And computing is about mathematics. So he was fundamentally a mathematician. And he developed this, he wrote this paper, The Chemical Basis of Morphogenesis, which is the creation of things. And this is where he combined all of these together, mathematics, physics, chemistry, and biology, all in one. And he said the purpose was to discuss a possible mechanism, because it is 1952, where he gave this theory, and it's been sort of vetted and tried and improved upon since then, by which the genes of a zygote may determine the anatomical structure of the resulting organism. So this was much more ambitious. So this actually didn't talk of these patterns as much, but it was trying to say the zygote is the cell, the embryo, the first cell, right? So how, the question he was trying to say, from that cell, how are we creating this structure? Right? A human is creating a human, a rat is creating a rat, a mice is a mice, a tiger is a tiger, which is very different. How from that single cell we are reaching this diverse and complex structure? Right? This is, if you see 52, this is probably before the DNA structure was known. We knew there were genes, but we did not know how the DNA was organized or structured. Okay, yes. So this is what he tried. So this was very ambitious. This is still an open question. But still, all sciences are being put together, including mathematics, and there are some principles of mathematics like topology, etc. I know Pushkar is a mathematician, so I'm also using some math terms here for his benefit. But there are mathematical terms and techniques which are being used to understand this simple phenomena, that from this single cell, how does this cell know when to divide into what? Maybe the DNA has it, but then how, at what stage it knows I have to create the right arm here, left arm here, it should be vertical. There's just so much choice and decision that is being made at every second from that single cell till even the shape of a human baby comes, right? 9 months to hai, but uske pehle even shape starts emerging, or another thing comes, right? It's any other mammal comes, right? Just the beauty of it. This question is just, I think, mind-boggling itself. Right? How is this happening? And it's still an open question. So that's what Turing tried to answer. But in that process, he actually developed this theory, which is now used to understand this biological pattern formation as one of the things about it. Now, we'll see a little bit, try and understand how is this happening. So if there is one such chemical, morphogen is a chemical, typically what happens, its concentration varies like this. And what we end up seeing typically are patterns which are very simple, stripes, 1D patterns, one-dimensional pattern, very simple structures. Now, if there are two such, then we'll have two such gradients, and it can create a little bit more complicated patterns, which are a little bit still geometric, as you can see, largely, but a little bit more sophisticated, quote unquote, or complex, at least, not just stripes, right? You can see they are different. But the third scenario is what he looked at. He said there are two different molecules and they are interacting in some way, which is what we are seeing. Like they are reacting, they are inhibiting, and they are expressing more. They are increasing excitatory and inhibitory. They are enhancing and repressing. So once that happens, then you can see a lot more complex kinds of patterns. Right? That's what his insight was, saying this is what is really happening. That there are two different chemicals which are interacting and they are also diffusing, they are spreading at different rates. And that is what is causing this magic of diversity to happen. Different patterns from the same phenomenon. And then, of course, he did his mathematical analysis. I'll go very quickly through this. So he developed these very complicated, or not so complicated, mathematical equations. These are always known as differential equations. At some level, it's very simple. He's saying the rate of change of one say V, this symbol. So read the English, forget the math symbol right now. What this means is that the rate of change of V, one chemical, is equal to at what rate it is getting produced, at what rate it is decaying, and at what rate it is spreading. Right? Very simply, it's very simple counting. It's saying at a given place, the rate of change of something is equal to how much is added, how much it degrades, and how much it spreads. That's it. Right? How much is added minus how much it decays plus how much it's coming in. This is the coming in term. So that's what this mathematical equation in English language is. But he framed it mathematically. And then, of course, what math allowed him to do was solve it. And with those solutions, he came to saying that there are 6 kinds of scenarios that we can see. And only one of them gives rise to these patterns. So there are very specific combinations of these parameters K and F, which will give us patterns. Otherwise, we won't have patterns between two. So maybe I'll show you that in some ways, right? So let me see if I can again take you back to that simulation, right? So now we are seeing some pattern here. Now let me do this. Let's see what happens. Yeah, almost nothing left, right? Slowly there will be no pattern. It will just be one plain, right? So this is what he found. This is what we are seeing in this simulation is that equation, and that's allowing us to play with it so wonderfully and see these different patterns, right? But only certain combinations. See, the pattern is gone. And now it won't emerge only once it's gone. Yeah. So any spot on your skin also you are seeing is something like this happened at least locally there. Otherwise, we have a uniform skin, right? Our skin is just another pattern formation place, just like a zebra or a tiger skin, right? So this is what he found. And this was the real, I think, insight that this mathematics brought, saying that there are only specific combinations of these chemicals or the parameters which will give us these patterns. And also sort of start predicting, saying what kind of now I need chemicals with which properties will these give me these patterns. Yeah, and that's what mathematics does. Now, once we know this, what did we as humans do? We can do now. We forget the skin. We can take any medium. We can take 2 chemicals and create now our own patterns. Right? That's what science allows us. That once we actually are able to learn, and that's what bio-inspired engineering is about. You learn from biology, abstract it out to this common phenomena like this reaction diffusion that's happening. And then you can develop technologies which mimic it, but with different parameters. You tweak it based on your need. That's what we are doing in various places and various things. And not necessarily all of that is good. I'm not saying that application is good, but yeah, that's what's happening. So math I'm not getting into, but I just wanted to bring this aspect of math out, that there is this one finally set of equations that can explain such diversity that is there on the back of it, by tuning in some parameters. Taking a pause. See, how is this sitting with people?
I probably have an unrelated question, somehow related, because you just showed the patterns and how they keep getting from 1D, 2D, 3D. And I couldn't help but notice that some of these designs look like flags of countries.
Yes.
So does that make USA the most complicated country?
Yeah, it's also one of the newer ones, right? Yeah. Yeah, so many flags are so simple, right? Just stripes of different kinds. Yeah. But how is this sitting? This fact, how is it landing for people? So we went from biology to chemistry, the different chemicals, to see how the physical phenomena of diffusion is happening, and then this mathematics. Yes, Bhavna.
So I'm just thinking this integration then allows us to kind of also predict. That's what he tried to do also.
Yes.
Right? It's fascinating. Like somebody is trying to think in those terms. So
yes,
I'm wondering what kind of a brain he must be having that you can like.
He's the father of computing. So all computing is what he is defined. That's the brain he had. And yeah. It helps with diagnosis, for example.
Yes.
Right, where things are going wrong.
You know.
And hence therapy. Hence, what can you do to correct it? So all of this starts happening once we understand this full science in some way, the background of the applications can be any which way you want. Yeah, Sandeep.
Yeah, I was also kind of saying that, so if you are able to observe the pattern of a disease and you understand the nature of all the chemicals or all the like herbs or medicines and all that, you can probably mathematically also be able to figure out that probability of this thing working here is more, and then try that.
Yes. Yes, Kalpesh.
So I was just trying to continue what Sanjeev said. Ki probability as well as the amount or the doses also may come from that, right?
Yes. Yes. The dosage, the concentration that is needed. And as you can see, sometimes to trigger this, you don't need much. Even one thing will then start the reaction. The process starts with just a dot. Yeah, you don't need. Yes, Jaya.
And also, I'm understanding that linear thinking is not something which will help in the cure of things, you know. So sometimes everything is so interconnected. So connecting the dots is very important there.
Yes.
So while a disease may happen in the body, but there is so much there, you know, in terms of chemicals, in terms of the physical movement, in terms of the chemistry.
Yes.
So I think it's very interesting to see that interconnectedness. That's what I'm getting to.
Yes, oh, that's fair. In fact, that was his insight, that there are multiple molecules, but they interact. And that interaction is what is creating this structure, the pattern there, in how they can inhibit, excite, what is inhibiting, what is excitatory, what is enhancing, what is suppressing. Yeah.
So Sandeep, you just said like the concentration may not be important, just triggering something to trigger and then things will automatically happen. Is that how homeopathy works? Because you take a very small concentration, it triggers something and not
yeah,
lot of believe that it works, right?
Correct. Homeopathy, but their conjecture actually is, and a little bit of the finding is there now. Even IIT Bombay had a paper on it, that it probably works even at a nano level. So at the nanoscale, so there are nanoparticles of the thing in that concentration, and at nanoscale, the physics starts becoming different. So the different laws of physics, the Newtonian laws don't apply anymore. So you have to work with quantum laws, and a very different kind of things happen, different effects happen. So yes, that small thing is triggering, but it's because of a very different phenomena in physics. Yeah, but it does. It can do that. So sometimes, actually, in physics, you see many times, then it becomes lesser. Less is more. When we say that less is more in physics, you actually see it happening. Sometimes less is more. That does happen. At nanoscale, it works very different. Yeah, Pankuri?
Yeah, talking about homeopathy, from what I've found out, another principle behind it is that water has memory.
Yes.
So yeah, I don't know much about that.
Water or even any good solvent. So they use alcohol a lot more than water. So yeah, that has memory. So memory is this of this nanoparticle, its essence, electromagnetic waves and properties of that. Yeah. That's what they have found in research also. So they have taken samples of these heavily diluted solution, kept it in a dark chamber, and they still find that it's emitting photons or waves of signature which belong to the original, like arsenic. But the chance of even one atom of arsenic being there is almost next to nothing, but they see that signature there. That's why they think it's memory. Like, yeah. Those experiments have happened. Yes, Bhuvna?
No, like we are talking about two elements, like you and we. I'm just thinking, can there be more than you and we?
Yes.
So that would that would bring in more complexity.
Yes, that would bring in more complexity. Yes. And mathematically also it will get more complex. So I don't know. Yeah.
Right.
And I'm sure researchers are looking at very much possible.
And
Madhuri
I
is saying
think
butterflies.
so
Yes,
from
probably that is seen. Yes, more colors. Yeah, Kalpesh. Go on. Sorry, Kalpesh, you were saying something.
I was saying, say from a zygote when a full body is created, like each body has say, so many patterns in it, and that probably there are multiple U's and V's, right?
Yes, of course. Yes, that though is there. I think what you were saying, even in one local system, there might be more than two. So in which case, even the math will change. That there will be a third equation and more. So it could be like one is inhibiting either both or only one. So a lot of cross terms will come in. Mathematics will get a lot more complicated. A lot more parameters will also get introduced mathematically. So it won't remain just K and F, because it's the interaction with 1 with 2 and 3. Right, then 2 with 1 and 3, and 3 with 1 and 2, right? So those are 6 parameters already from just 1 and 2, and 2 and 1 is mutual parameters.
Yeah. Then Sandeep, in the context of our body, then is that what our glands or endocrine system is doing? It's kind of looking at this chemical compositions, patterns, and then releases activators or inhibitors to bring balance and cure and everything.
Yes, totally. Those are the chemical sensors. So these are known as chemical sensors in our system, and exactly how they respond to the concentration of various chemicals. So they will open channels in the membrane. They will open secretions of various hormones, various neurotransmitters. All is this managed by this cycle of concentration. Correct? Totally. And blood is what is moving this concentration everywhere.
Yeah. Yeah, blood is the...
Yes. And then it triggers the autonomous nervous system based on certain things, right? So autonomous nervous system has its own triggers, based both chemical as well as other triggers. So autonomous nervous system is governed by many things. So chemical input is definitely one of them. And that's why food is also very important, because food is a direct source of chemicals in our body.
Yeah, increasingly they are relying a lot more on food and how to, use it as medicine.
Yes. That was, I think, Hippocrates also, and of course our Ayurveda says that. Even Hippocrates, the originator of Western medicine, says, "Let food be thy or be thy."
Yeah, Ayurveda is totally based on that. Lot of it. Yeah.
Okay. So I think if there are no more questions, I'll share one, I think, thought process that what this summarizes, and I think from there, where we end to this chain. I have also left a link here of a video. You can see this. It's a 5-minute video. If we have time, I will share that. But this is what I see as sort of the chain of science now, right? So what we saw, we started with biology. We saw a large number of diverse patterns, right? So very high diversity, very high multiplicity, such difference that sometimes it's hard to imagine there is anything unifying or one in it, right? Then we saw the source of this diversity was different chemicals which are playing very similar function, right? So there was similarity in function, but there were still quite a few. There are still many chemicals which do that. It's not like something we can count in our hands or fingers. It's still numerable. It may not be as diverse, but there is still quite a large number. And then we started looking at the physics of it, right? Where we saw the physical phenomena of diffusion and binding, which is just two physical phenomena which are happening, but their parameters, the rate at which is happening, is different. So that's where the space and time dimensions are coming, right? That's where this physical property of these chemicals, of different chemicals, is creating this diversity, right? Just two phenomena, the two physical phenomena is causing such diversity. And of course, it is in the solution, in the environment of the electrolyte of the liquid that's there in biology, which is very different. In water, it will behave very differently. We can't create the same pattern in just simple water. The liquid that we have is different in which all this is happening, right? The solvent itself, which is another chemical here. And lastly, then we saw how this equation of two chemicals with multiple solutions, right, is causing this diversity. So from this high diversity, we came down to this one unifying equation to integrate this phenomenon, right? What otherwise seems so diverse and complex, as we keep bringing it out, we can keep narrowing it down, and that's the hunt. That's the hunt, basically. So it goes from this very concrete biology. We see such difference, such diversity across. But when we abstract it out, it starts becoming unifying, right? So from concrete to abstract, from tangible, very touchable, to a very intangible thing. Those equations that U, V, like those are variables. That's the algebra we learn, right? So those principles of mathematics come from very gross to very subtle, right? So that's what we see in our yoga also, right? That at gross level, it's so diverse. But when we talk of our unifying principle, it becomes very subtle. From very concrete, each individual is very different. We see such diversity. Each element is so different. Each cheetah is different. Cheetah's prints are different. Everyone's fingerprints are different. To that one common unifying factor across each one of us. Right? And that's what this sort of, to me, is like the chain of science. This hunt, this search, this movement from this concrete to abstract, from the gross to subtle, is what to me is this chain of science. And this is what scientists tend to do. And so one way of seeing this chain of science, the other way to see this is like an inquiry, right? An inquiry of what? It's like an inquiry. So to me, biology is the life that we see around us, which is there. It's like a story. So it's like I've been given a book. We can see it that way, right? It's a book which is written in a language I don't know. But the entire story is there. It's out there, it's inside us, the same story. The whole story is there, but we don't know the language. The chemistry is giving some words and sentences, right? And we start making out the chemistry in which the story is written. So we start some words, acha, this, that, oh, this is metabolism, this chemical is linked to this chemical is linked to that. And what physics gives us is the rules, I think, or the grammar, what connects these words. Right? If this is what role is it playing? Like, is it a verb or a noun in this context? Then the story starts making sense. Like, the cat drinks milk, or the milk drinks cat. I may know the word milk, cat, and drink, but that sentence, what is happening, what I won't know. Or a man eats a tiger, or tiger eats man, for example, right? And finally, what mathematics gives to me is the alphabets. And how to bring them together to make some words, to make some sounds. It's the ABCD, basically. And that's what enables us to understand this beautiful story that's out there in life. That's one way. And to me, that's what science is really about. It's this inquiry or the inquiry. So I use both because I think inquiry is external and inquiry is internal. I'm using that E and I in that sense. I don't know whether that's what it means in English. I'm taking the liberty here. But you either inquire in the external or inquire in the internal. But the purpose is to decode this language, is to understand this language in which the story of life is expressed. What's that unifying thing? How do I understand all this, make sense of this? That's what science is. And it can be done in a lab. It can be done sitting at your home. When you do inquire, whatever suits you. That's sort of the language of nature. And this phrase of language of nature actually came from a Nobel Prize winning scientist, physicist called Richard Feynman. Some of you may have heard of it. He says, if you want to learn about nature, to appreciate nature, it is necessary to understand the language that she speaks. Otherwise, we can't really understand nature also. You talk to it, and different people do it in different way. Obviously, as a scientist, he says this is the language. That's what I have tried to also share here. But each of these has such beautiful, I think, meaning to it. We'll take a pause here, see how this is. Does it make sense? I see Bhuvna's hand is up, so go ahead.
So I'm just thinking about those fractals.
Which fractals?
Fractals.
Okay. In general, fractals.
In
yes.
general, fractals, and how they say that, life evolves in the form of spirals, and how in nature everything gets replicated.
Yes.
So, I don't know how to hold all these things, but this session is kind of bringing at least this process in this process. It's fascinating.
So you know what fractals are?
Honestly, I don't know. I know the word.
Okay. So the Jaya, go on, you know.
No,
I
it's
was
Greek
just
to me. I don't know.
So what did you say? What were you saying? Agree?
I said it sounds Greek to me. I don't know what it is.
Okay. So fractal is it's a math concept originally, and it's become very popular, which is great. But fractal is a pattern. So what happens, you through a mathematical equation, you create a pattern, and the nature of that pattern is that the more you zoom into it, so you zoom in any part of it, it will look the same.
Yeah.
So you keep zooming in, it will look the same. So let me see if I can quickly. Mandelbrot set is one of the most common fractals. Let me see if I can quickly find an example of it. I hope this allows for zooming. Practical. Oops, sorry. Yes, I did get something. So let me share my screen and show you that. And that's the beauty. I think this is very much related to our yogic concept of the macrocosm is the microcosm. So yeah, you can see the screen. Yes. I think this will show that I haven't seen this video before, but I'm trusting it. So you can see it zooming in. Oh, let me start again. So see, this is the macro pattern, yeah? Okay. There are many. And this is, when they plot this, they basically take one equation and it just take it at any value, and you can't take out a section block of it, it will look very similar. And so fractals have dimensions, then obviously the math starts abstracting out more and more. So then fractal science or fractal mathematics is a whole branch in itself now. Yeah.
Now I understand bio and math a little more, Sandeep.
Yeah. And hopefully the connection that they are all.
The connection, yeah. Connection and how.
And how?
And how it's applied to our, day to day.
To me,
So
okay, Sanjeev, finish.
Sorry, I was just saying that, like knowing and knowing to this level helps us understand, but it also in a way tells us that how all that intelligence is inbuilt in us. And if we learn how to not interfere with it, let it play, it is kind of self-healing, self-curing and all that, right?
Yes.
We just and maybe that's why meditation is probably so effective, because it helps us relax and not interfere with its intelligence.
Yes.
I have one question. When you say we interfere with that, what is we? Like it is the same biology which is interfering with that same biology, right?
Yeah, in one way, yes, but we get trained like as society is evolving, we are observing, learning, and then we see something, we try to mimic it. It may not apply to us, right? Because I am different, everybody is different, but we try to do same thing.
Yeah. So I think a difference, to answer that, respond to what Kalpesh is also saying, is that there is a part of us which is driven by this biology purely, which is evolved, right? Which is the whole physiology. But having said that, our evolution as humankind also has resulted in a part of us which doesn't exist with others, which is the neocortex, this part of our brain, which is not there in other mammals or entities, right? And that has a way to learn, to store, to try and quote unquote interfere in this language, to try and optimize. And it works. It works in many which ways. It's allowing us to even understand this, the concept of mathematics. All that is coming because we have that component, but that can also be overriding sometimes. And that's what I think when Sanjeev is saying, in my understanding, that's what we have to find the balance of. It's not saying, oh, we don't use this completely, because then we won't be human. We'll just be living by that instinct. But to use this, but also know when not to, right? To when let things be. It's finding that puts an extra onus on us, right? This sort of unique, you can say, feature that we have. And this is evolved in the last, 900,000 years, less than 1 million years. Very new. In a 4.3 billion year history, less than 1 million years is very new. So we are still learning how to use this. We are still evolving with this, right? So this is new. And this is like, there is great evidence which says why this is new. Like every other species, this area itself, you see the brain is at a different angle. So ours is very vertical. If you look at others, it's this way. So it reduces the volume only of this brain by 30-40%. And there is nothing here. So the next nearest entity that you will see, all apes, etc., this is not there. Their brains, the skull is like this, it's slanted, while ours is very vertical. So this gives us some unique abilities. It allows, for example, we can override our autonomous nervous system. We can override our instincts many times. It gives us that privilege, but it also can cause problem there. So that's the balance we have to find. I think that's the tricky thing for us. Yeah. Jaya was saying, Sita says, yes, that reminds of Sri Yantra. I think a lot of our yantras are very much, I think some patterns, these fractal patterns, energy patterns, that they were discovered, not necessarily through this detailed analysis, but maybe through a different process as well. Reminded Krishna's darshan to Yashoda. Madhuri says, yes, that in the mouth, the earth, the whole earth being inside the mouth of fish. Jaya, yeah, you were saying something earlier.
To me, the way you presented the biology to maths, speaking of it in terms of language, to me, I was getting a different thing. To me, biology is life.
Yeah.
To me, chemistry is relating in any which ways. And to me, physics and movement for relating for life, whatever. And maths is that abstract DNA we have no clue of. I mean, that's how I looked at, the connection between these. And also, the connection to nature that the last quote spoke of, so that is why the shamans in some earlier age, they were so knowledgeable because they were so much in touch with nature and the intricacies of how nature works.
Yes.
So they were so very, I mean, in the healing process, they were very, very effective.
Yes. Yeah. And I think that's why I like that quote, because it is generic. So one of the languages is this, the language of science, but there are other ways to communicate with nature. Language is for communication, but what the intention, even the more abstract intention. So this is what the scientists do. This is the process they are following, or the language they are trying to understand, the way they are trying to interact. A true scientist is, but there are other ways to interact with nature. And that nature is both outside and inside us, right? So whatever works for us, whatever works for everyone.
Yeah.
But we need to know that language. That's important. We need to search for that language. It's like really accepting it is new. To decode, to be in that inquiry mode, to be curious about it all the time.
Yeah, I mean, with science, we try to go at a very, very micro level because it helps us understanding what is happening. But biology is at a very macro level, like, so many variables, how they are mixing and interacting, and how do we kind of regulate it?
Yeah. So yeah, any other closing thoughts as we close the session?
So reminds me one of the quotes. Sandeep said that biology is applied chemistry, chemistry is applied physics, and physics is applied mathematics.
Yes. Yeah, that's the reverse chain. Applied or very, very contextual, very specific. Yeah. That's very special kind. Yeah. As we close, good to hear from everyone a little bit, one sentences as we close, particularly people who haven't spoken much. So would love to hear how, what is staying with you, what is sitting with you, what are you taking away?
Differential equation will always stay with me because this is something that I was not knowing that why differential equations are used. So frankly, we teach everything mechanically, I think. So for me, this differential equation will always stay with me.
Thank you. Yes, the power of equation. Yes, Bhumna.
I completely agree with Pushkar because until now I really didn't know why we were using all this differentiation integration. And this the way you connected biology and chemistry, physics, and then maths, this is really fascinating. I have never looked at these subjects in this way. How can you connect? It was all like, padlo, exam likhlo, then you're done, to bringing it to life. Thank you so much. This is proper integration. Thank you very much.
I think I'll go next.
Yeah, please.
Gopesh, then Amrita. Go ahead, Gopesh.
Sorry. Yeah, so for me, please go ahead. Someone is trying to say something.
Gopesh, you go ahead, then Amrita.
Okay. So for me, just as Bhuvna said, how these sciences get linked, I think that was very beautiful. And another thing which would stay with me for quite some time is the question that you started with, which was posed by Alan Turing, which is, how does a zygote know the shape and form it has to take? And I think just that question is so refreshing to think about.
Yeah. It is.
Thank you.
Thank you.
Yeah. Hi.
Yes.
Sorry for interruption. So basically, the whole concept was pretty heavy for me to actually, frankly, to digest. But then, yes, there are certain things which I could relate to when we come to the real life. There are certain general rules that we follow from our traditions and our general, what do you say, the ancestral, like you just were explaining about the forehead, right? Slanting one and the flat one, the vertical one, something of that sort. So I remember people used to figure it out with the king's face, how is his forehead, and try to figure it out how what his personality will be. So even the other sciences, probably the palm, how do you read the palm, the face? I guess even those sciences are pretty much attached to this. The second word that I could really, attach to, because that is something close to my heart, is nature's language. I'm sorry, this little noise behind me.
No, it's okay. Go ahead. We can hear you.
Okay. So basically nature's language. So yes, we feel that, they are always in a calm or a composed manner. The tree won't move, but I just went for a waterfall, and then we realized that when it falls from above and hits the ground, it makes noise. So that is probably the nature's language. You also have to react when you hit a stone or you are falling from somewhere. You will make a noise. So it's perfectly normal to react or respond to a situation when it demands. So even nature's language is, something I could connect to when you said that in the last slide. The rest of the slide, frankly speaking, was very heavy. I'm a commerce student, so neither biology nor engineer. So for me, it was a little heavy. But yes, I was with my son, who is just 11 and 12, and he's really curious on chemistry and physics topics. And he was asking me certain things. We were discussing few things, and we really thoroughly enjoyed, the learnings out of the whole concepts. Thank you so much.
Thank you. Thank you. Yes, Pankuri.
What I will take with me is that what makes all the difference is the interaction between all the molecules. It's very important.
Very nice. Thank you. Yes, sir.
I think I just had one word, it's just like wow. Seriously, wow. In terms of everything is so related. And I'm a biology person, but then that chemistry was not making sense. And then the last slide, like there was also language in English, and then somebody was talking about history. So everything is so related to each other, and all of us are moving towards artificial intelligence, people, but there is so much beauty in natural intelligence. Like we are not going back to our roots. There is so much that we need to find out about ourselves before like looking for other things. Beautiful, I would say. And I know my sincere request, Sandeep, you should write a book. I think many more people need to kind of enjoy this wisdom, and maybe this thought process of thinking beyond our thinking is like kind of opens up. So amazing.
Thank you. For now, share this video, I guess, with whoever you want to start with, or the previous ones or the playlist. Yeah, but we'll see. Yes, Malish.
Sandeep, have you read Richard Dawkins' Blind Watchmaker by any chance?
No, not that one.
So it's very interesting. It starts with similar equations and simulations on, how starting with a dot and a dash, different shapes can evolve.
Yeah.
And after some time, these shapes begin to look like biological beings. You can't really say what it is, but, very much like biological beings, right? Governed by similar differential equations working in the background. and it sort of connects, everything to evolution. And I found, Sanjeev was saying, I found a very spiritual connect there, because the blind in the blind watchmaker is that the nature does not really have a plan. It is, sort of just evolving. It is our connotation and interpretation, that we want to, see everything having a plan, purpose, and a meaning. Truly, so it's sort of it's very scientifically, very very similar explanation, but it's also spiritually very relieving, where because you stop blaming yourself for everything around and carrying that the weight of the whole world and of your own ambition as well as everything happening around in the world, right? So it's pretty awesome. I would recommend everyone read the book if you found this fascinating.
Thank you. Yes, sir.
Yeah. For me, Sandeep, what I think is really stood out and will stay is the connecting with nature and understanding nature language, right? So the more we relate to it, it's probably is going to help us understand us more and be relaxed about it and not worry too much. It's just naturally bring us at ease.
Yeah. Thank you.
And yeah, I echo that too, that writing is, you should write a book.
Pooja, unmuted.
Thank you so much. I think this was completely new. It was like, okay, what is happening? I don't know. Yeah. The big takeaway I'm actually taking it with me is, I think any small addition to our body, good, bad, I think it's going to create that reaction. And I don't know what impact it will have in the overall body. So I think need to be more careful in what we are doing. Yeah. Thank you.
Thank you. Most people shared. Sita, Sean, Sindhu. Any words?
And next time, if possible, please conduct a lecture on algebra also, so that I get to know what is algebra.
That you have to do. Yes. Yeah, Sita, you were going to say?
What stays with me is the inquiry to inquiry part, the gross, the subtle. And as Pooja said, I'm looking at the ripple effect kind of which will be created within. Yeah, those are things that I'm staying with. And as I think Amrita was the one who shared, yeah, I'm still taking time to assimilate. I do appreciate the beautiful integration and the way everything was connected. I'm taking time to assimilate everything.
Sure. I like this. Is the inquiry from the gross to the subtle, right? That's what you said. The volume was, yeah, very nice. Yes. Okay. So Sharon is saying, I'm staying open to do more self-inquiry. Thank you. Yeah. Okay. Lawson, how does a cell work fractal maths? The cell will be something that I'll try and look at. Good. Any other? Sindhu? There's only one, like, if you want to add, or we'll close the session. There's nothing more.
So my suggestion also would be like maybe Chaya and Sandeep would prefer books. We would like to have short videos, which makes it easier for us to grasp. So give us some basics, fundamentals like ABCDs, and then move on to the larger parts of it.
In fact, I'll share the link for at least this. There's a short video on this particular pattern thing. But anyway, to me, I'm glad many of you have taken that away, that the important is to inquire into the language of nature. This is one such language that science uses to inquire into. And the example of patterns was, I think, just one pattern which you started to understand. I think the specific example wasn't that critical to our lives, but I think this thought, and many of you are taking that away, so that gives me a lot of, at least, joy that that's the takeaway, that inquire, that small things make big difference, because there is a thing, there's a whole sequence around it. So yeah, it's good. Thank you. Amruta, you wanted to add something?
No, I was just saying that if not a book, you can at least start with a blog or something which will help us. That will be a little smaller and easy to digest for us.
We'll try. But yeah, good. No, I'll try. And as you watch this again, please feel free to ask me questions. You know that, so you can message me as you go through this. If there are more thoughts, always welcome, either on the group or to me as well. So happy to stay with that. It will also push me to make it simpler, make it more relatable. So I think I'm also learning how to communicate this. There is just a lot. You can't believe how much I have cut out. There were two more examples which I just chose. No, not for today. Let's do only one. That's good enough. There are many more. So please push me. So please, if you can, watch the videos again, and if there are more questions, comments, please do share. Okay, yeah, Sindhu will watch the recording again. Feel free to share. Let's try what the mind does not know, the eyes do not see. Thank you. Okay, nothing more. We'll close. Yeah, we'll close with a prayer. Just give us a minute more. A good prayer, reminding ourselves that it's about, if we want to understand the nature both inside and outside, that's what we need to do. We need to understand the language that she speaks in. So this is from a Nobel Prize-winning physicist who is known for quantum mechanics in the modern day world. One of the best teachers of physics, I think, still date of time. His lecture notes on physics are still the most popular, both textbook and the video recording. He's recorded in 1960s, but we still use it today. Any physicist who wants to learn physics, he has to read them. So that's the guy again. So okay, good. So sit comfortably on a chair. Let your feet be comfortably on the ground. Your back supported. Gently close your eyes. Bring your attention to your breath. Notice the air going in and out. Repeat after me. May all be sukhi, khush, joyful. May all be swasth, sehatmand, healthy. May all be in shanti, sukun, peace. Thank you, everyone. Have a good Sunday.
Thank you.
Whatever is
Thank you,
left.
everyone.
Thank you.
Thank you, Sandeep.
Thank you.
Thank you.
Thank you, Sandeep.
Thank you. Bye.
Thank you very much. Takes a lot of effort to put a class like this, Sandeep. So really appreciate it.
Thank you.